Right then, year 13s. So it's chapter 6 still, and we're looking at oblique impacts in the section on impulse momentum. And you'll notice that, if you actually look in the book, very little of this is AS. But I will just introduce the A2 work just because it follows on from something else we've been doing. The principle is simply this. If an object strikes a fixed surface, now imagine in this case we're looking down on something, so we're not considering something falling and gravity, so we're looking down on a wall or something. When it strikes, there will be we can incorporate the coefficient of restitution in the impact, but the key thing will be that the impulse is perpendicular to the wall. Okay, impulse is perpendicular to the surface. So if an object has these two components of velocity, after the collision, this one will be unchanged, and the other one, this one, will be in the opposite sense to that, and it will also be that multiplied by E, the coefficient of restitution, where E is coefficient of restitution. So what have I said there? I've said that the impulse is perpendicular to the surface. So V equals EU, perpendicular to surface, where U and V are speeds. If we're talking about velocities, we're going to change the sign of this one. And parallel to surface, nothing changes. Right, how does this split up? With the AS work, we do it in vector notation, i.e. components already given. At A2, we'll use speed and direction to calculate components. And by all means, if you want, read ahead on page 149 and 150 and things to look at that, because you will notice in terms of what we need to do this year, it might be we just do this as immediately the next topic. I'm just going to chat to the others. When you look at the exercise, questions 1 and 2 are the AS ones, and everything else is the A2 work. But since the concept of the A2 work is so easy, some of you may well want to, once you've read this and this, the AS bit, you may then want to work through the A2 work to see if you can answer them. We will make time to do the A2, or you might constructively use the time to look back at what we have been doing already. Right, I'll just look at one of the examples then. So I'll look at the Worked example 6.2. A smooth vertical wall is parallel to the positive I direction. So there is a wall. A smooth sphere of mass 3 kilograms moving with velocity 3I plus 5j. So a ball moving with that velocity, 3I, 5j. So that's the initial velocity. Collides with the wall and rebounds with velocity AI plus bj. So it rebounds with velocity AI bj. Given that the coefficient of restitution is 0.75, I was going to write mu there, that would be bad, E equals 0.75, find A and B. Simply this. Parallel to wall, no impulse. Therefore, well, parallel to the wall is this way. So we've got A equals 3. Perpendicular to the wall, Newton's law of restitution, which means that B is whatever that is, with the sign changed, multiplied by coefficient of restitution. So 3/4 of 5 is well, I don't agree with the book there. So 5 on 5 times 0.375 equals 1.8. 5 times 0.75 equals 3.75, but negative. So the final velocity is 3I take 3.75j. Other questions they could ask, because they should really, because we've covered these other ideas. If they wanted to know the impulse is a vector, is mv take mu, which in this case would be a mass of 3 I just keep reading the question to see if they didn't mean 0.5, but it's just wrong there, isn't it? Yeah, they've just got it wrong there. So the impulse is going to be 3 times this take this, so 3I take 3.75 j take 3I plus 5j, which is 3 lots of the I component disappears, and it should do. If the wall's parallel to I, there's no impulse in the I direction. So we've got 3 times minus 8.75 j. 3 times 8.75, 26.25 j. Impulse is measured in kilogram meters per second. Or it's measured in Newton seconds. So in this case, the magnitude of the impulse, it's only got one component, so that's 26.25 Newton seconds. Question could ask you for a change in energy. Remember, kinetic energy is half mv squared, where v is the speed which is the magnitude of the velocity. So in this case, for this question, the loss in KE would be half times 3 times, it's got more energy before a collision than afterwards, will be one of the things we always find. So we've got the initial. Now notice, since we're squaring the speed, and since speed is the magnitude of velocity where we're square rooting the sum of the squares, squaring that means we get rid of the square root sign. You might have to rewind that a couple times to make sense of what I'm saying. So we're going to get 3 squared and 5 squared for the initial speed squared. Take 3 squared and 3.75 squared for the final speed. Now in this case the 3 squares are going to cancel, so what we're going to end up with, we're going to end up with 0.5 multiplied by the 3 multiplied by, I'm sure I should be able to do this in my head, but I'm not going to, 5 squared take 3.75 squared. And if I find any of you suggesting you can do 5 take 3.75 then square it, you need shooting 16.4 joules. Right, and should we be clear on this? Vector, 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 scalar, scalar, vector, 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 magnitude of vector, so scalar, 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 scalar. Right, have good luck with exercise 6b 1 and 2. Next week there's going to be scope to doing some Zoom lessons, okay? A lot of things fall into place for next week, so I'll invite people back to, the Microsoft Teams lessons next week. MS Teams, okay? And I want to be sending out some past paper questions from a lot of these topics. Right then, take care.